Okay, so this is a continuation of Unit 2. This time we're going to be focusing on atomic structure. We finished with the last section on the nuclear atomic model, and we're going to be using that to talk about how to calculate the mass number and how to find the atomic number on the periodic table. We're going to give a very brief description of the periodic table in terms of its classification and things like that. And then we are going to look at the types of elements, the charges that elements might have if they form ions, and so on. And that's going to lead us into naming and compounds. So we're going to start with the overview of the atomic structure. We're going to look at how the isotopes have the same atomic number but different mass number, and that's because they have a different number of neutrons. We're going to look at how ions have different number of electrons, and then we're going to look at the periodic table's organization. So we ended with this slide last time, and I just want to point it out again. We now believe the proton and the neutron are in the nucleus. The proton has a +1 charge, the neutron has a neutral charge or no charge, while the electron orbits the nucleus in orbitals that we will talk about much later in the semester with an overall charge of basically a -1. So the charge of the atom comes from protons and electrons. The mass comes from the two larger subatomic particles, the proton and the neutron. Now, because the nucleus has these much larger particles, it is dense and much smaller in relationship to the overall atom. The atomic number, or we usually use the letter Z to denote atomic number, indicates the number of protons. Now, when you take my exam, this is the periodic table you will get. You can kind of see there are no names on this. However, there are lots of numbers. So the numbers at the top are our atomic number. The numbers on the bottom of the elemental symbol is the atomic mass. And we'll get to the difference between atomic mass and mass number later. This is the periodic table you guys will get. It is the standard table given on AP chemistry exams. I do expect you guys to know the elements and their names. If you've had chemistry before, most high school chemistry classes expect you to have a periodic chemistry test on that at some point. Now, getting back to this, the atomic number is just given from the periodic table. It's the same for every atom of an element. Every single hydrogen has an atomic number 1. Every single helium has atomic number 2. It's going to have 2 protons. The mass number, on the other hand, is going to be equal to the number of protons plus the number of neutrons. Those are the two large subatomic particles, and the number of neutrons can change. And when it does, you have an isotope. So, for example, you can have carbon that has a mass of 12 or carbon that has a mass of 13. Now, if you have carbon that's got an atomic number 6, they must have 6 protons, period. That is just truth. But this mass number is protons plus neutrons. Oops, there we go. So if we have 6 protons plus some number of neutrons equals 12, we can solve by subtracting from both sides, and we get 6 neutrons for this guy. Over here, 13 minus 6 protons. This is protons plus neutrons. This is protons. Gives us 7 neutrons. Now, the way that it's written on the periodic table is to put the atomic number on top, the mass number on bottom. However, the isotope symbol puts the mass number on top. So you're going to have the element symbol, mass number, and atomic number. This comes from the periodic table. This is protons plus neutrons equals some number. So for us, we would write carbon 14 like this. We would write oxygen 18 like that, and so on. So what's the mass number of an atom of oxygen containing 10 neutrons? Now oxygen come on, there we go. Oxygen is atomic number 8. That means it is going to have 8 protons. So this is our protons. This is protons plus neutrons. We know we have 8 protons. We have 10 neutrons, so this should be 18. And so we should have oxygen 18, or you could write it as oxygen 18 with the atomic number on the bottom. Either way is acceptable. An element has the atomic number 14 and a mass number of 29. If we look at the periodic table, number 14 is silicon. So we're going to go back. We know that 14 is silicon, and it has a mass number of 29. So we can write the symbol this way. We know that it's silicon because it has 14 protons. That alone tells us everything. Now, because its atomic number is 14, it gives us 14 protons. Now, it is neutral. There's no charge written here, which means that the number of positives have to equal the number of negatives to give us a neutral atom. So if we have 14 positives or 14 protons, we also need 14 electrons in order to cancel. In addition, if this is protons plus neutrons is equal to our mass number, this is protons. To get the neutrons, we subtract and we get 15. An element contains 2 plus. An element 2x2 plus contains 20 protons and 20 neutrons. Now let's just write this out. 20 protons, 20 and 21 gives us 41 mass number. What is the atomic number and mass number of the element? Atomic number is just the number of protons, so these are the same. So it's going to be 20. Mass number is going to be these two combined, so it's 41. What's the symbol? The only thing we're missing is what this X is. So if we go to the periodic table, we can look up number, we can look up number 20, which is calcium. And we can then come back here and write it as calcium 2 plus, preferably with your 41 there as well. So that is how you calculate mass number. You write the symbol for isotopes. And, honestly, let's go back here for a second. Let's look at the number of protons, neutrons, and electrons. We have 20 protons. We have 21 neutrons. The number of electrons, if it's 20 protons, 20 positives, it's calcium. Overall, this guy has 2 plus, which means we need to have a discrepancy between protons and electrons. So we only have 18 negatives. 20 minus 18 gives us a 2. So we can determine our electrons that way. So guys, make sure you are comfortable calculating mass number. Make sure you're comfortable going from looking at how isotopes change in neutrons, how ions change in number of electrons, and so on. I'm going to spend just a little bit of time on the periodic table and just point this out real quick. Now, most of the periodic table is metals. You have the metalloids, which have properties of both right here. Everything to the left are metals. Everything to the right are nonmetals. Metals are shiny. They are malleable. They are ductile, meaning you can pull them into wires or you could hammer them into a sheet. They conduct electricity. They are metals. Nonmetals tend to be brittle. They are not shiny. They're more dull. They do not conduct electricity. Now, generally it's kind of hard to think about these as metals, but if you were to take, say, I think Raisin Bran in total have a really high amount of iron in them. You can actually take a magnet, put it in a Ziploc bag, and smash it to the bottom of the cereal. And when you pull the bag back out, the magnet usually has a lot of cereal stuck to it because the metal that is in the cereal is stuck to the magnet. And so it just kind of reinforces the idea that it is metal. I mean, there's calcium, iron, and all kinds of other things in our diet that we absolutely must have. Now, we can also talk about the periodic table in terms of groups or periods. Now, the groups are numbered one of two ways. For the most part right now, I'm going to number them as 1, 2, there we go, 3, 4, 5, 6, 7, 8. Later on, we'll deal with the properties down here, but for right now, that just makes it a little easier for us if we number straight across. The properties of elements within these groups are very similar, and we'll talk about that in just a minute. Periods, on the other hand, are these rows, 1, 2, 3, 4, 5, and so on. And these have, because they go all the way across or across many columns, they have variable properties. Now, in addition, let me go ahead and erase this because we're going to come back to it in a second. We need to talk about the overall groups. Alkali metals are this group 1. They are incredibly reactive. I used to do demonstrations the first day of class with sodium and water. In fact, in high school, my teacher, this was before a lot of the regulations were in place, my high school chemistry teacher had this huge chunk of sodium that was probably the size of, I don't know, a small puppy's head, or probably bigger than that. And she had it in this huge mason jar, like the dill pickle jars, and it was covered in oil. Oh, Emma, okay. Where is pause? Hold on. Okay. Let's pause. Okay, so we have the alkali metals. We were talking about the solid sodium that my chemistry teacher had under oil. She had to keep it there because it will react so violently with water in the air. And I can remember the second day of class, after, she scared us with safety and so on, she used a butter knife and gloves, goggles, all of that, reached into the mason jar, and while the sodium was under the oil, she used the butter knife to cut off a little piece of that sodium. Maybe like a small piece of gravel size. And she drew it out, had this hood with a small beaker of water, and she kind of tossed it towards the beaker, slammed the hood shut, and ran past us all the way to the back of the room. And so we were kind of thinking, oh no, now what? And sure enough, as soon as the sodium and the water contacted, it does take a couple of seconds for the oil to get off and them to react. But as soon as the sodium and the water make contact, there is this huge reaction. You get flames, you get sparks, you get all kinds of fireworks, essentially. It's pretty awesome. Since then, chemical companies have gotten a little smarter. Now they sell these really tiny pieces of sodium for us to do demos with. And even with those, once I managed to, get a small fire in a hood going, because the reaction is so strong. The bubbles and the flames actually force the sodium out onto a piece of paper towel in the hood. That paper towel went up in flames, but it was a good experiment, good fun. Now, in general, the further up and down you go, the properties tend to get more or less intense. So sodium is about as strong of an alkali metal as I would want to deal with. Now, all of these guys have a charge of +1. They have one valence electron, which we talk about later, but they need to lose one electron to look like the noble gases. So they're all going to form a charge of +1. The alkaline earth metals in group 2 form a charge of 2+. These are a little bit less reactive than the alkali metals, but still pretty reactive. Now, both of these have alkali or alkaline in their name, and that's because when they react, they tend to react to form pretty good, reasonably strong bases. Group 3 forms a charge of +3. We don't worry about the charge for group 4. Technically, the metals down here will have charges, but we'll talk about that later. Group 5 has 1, 2, 3 steps to make it to group 8, so this is going to gain 3 electrons or have a 3- charge. Everything in group 6 is going to be 2-, 1-, and we don't worry about the charges here either. Now, the halogens. This group right here is called halogens. They tend to be happiest when they're together. In fact, if you look at the Hofbrinkels, these are the elements that are only going to exist in nature as diatomic elements. You're never going to see oxygen floating around. You're going to see O2. You're never going to see nitrogen. It's always going to be N2. Most of the Hofbrinkel or diatomic elements, fluorine, bromine, iodine, chlorine, these are all halogens, so they like to be diatomic. In addition, we have these transition metals. Now down here, including all down here, which these are the ones in group 4 I said we wouldn't worry about. We've got to deal with them as a transition metal. These can have variable charges. Now when we get to unit 7, we talk about why the charges are what they are. For right now, what I want you to know is that these have variable charges. They could be +1, +2, +3, all the way really up to chromium will occasionally have a +6 charge. Now, with that in mind, we're going to have to deal with that when we make compounds. Also, noble gases, this group 8, are unreactive. They tend to not want to form compounds very often. So a halogen in the 5th period. You go 1, 2, 3, 4, 5. Here's the 5th period. Come over, and we find the halogen in group 7, and it's iodine. Alkali earth metal in the 3rd period. 1, 2, 3. Alkaline earth is the 2nd column, so it's got to be magnesium. What charge do halogens usually form when they make an ion? So because they are in group 7, They have one step to go. They need to gain 1 electron, so they're going to have a charge of -1. Do metals want to form positively or negatively charged ions, and why? So they're going to form positive ions because they're going to lose electrons. That is really it for the organization of the periodic table.